Before I show you how to add a pressure vessel to this model, let's take a step back and look at what we are doing in the broader context. We are seeing that even overnight at 1 a.m, when there is little customer demand, pump power failure creates unacceptable low heads at the highest locations in the reticulation network. That trace graph was referring to these highest locations in the system. And in the last part of the engineering mission, we analysed the effect of placing a 25mm Ventamat air valve here. It delivered a marginal improvement in minimum head in this local area, but that's all it achieved. The network operator is not likely to accept a recommendation to install lots of air valves on the reticulation pipes. It is a solution that delivers only marginal benefits while creating added maintenance and operation issues. Customers want to receive water through their taps, not an occasional mix of air and water. All I have really taught you is that it is very easy to add air valves to a model and analyse their impact on a system. We will leave that one air valve in our model and change our mission to testing the impact of placing a pressurized air vessel on the pump station's delivery manifold. You can do that by using the File menu to return to the editor if you are not already back in the editor. I am. In Edit mode, zooming over to the pump station and turning on node labels. Here's node 80, where the pressure vessel is to be located. We need to use the right side toolbar to add a pressure vessel. Pointing to the node, clicking the Add Pressure Vessel button again to stop adding pressure vessels, right-clicking the pressure vessel symbol and selecting Edit to set its parameters as air volume, 0.5 cubic meters, water level 72.57, and cross-sectional area 1 square meter. You will find these values make sense when you model the geometry of a real vessel. Saving those data changes. Swapping into Simulate mode, starting the transient simulator, selecting the event 1 a.m. Now that the simulation has run, activating the source to summit route, browsing that route, setting the vertical scale, and playing the animation. Apart from oscillations in the suction main between the source tank and the pumps, the delivery system gracefully is coming to rest. The transient head envelope is quite acceptable. Closing that hydraulic grade line, activating the Summit to Node 420 route, browsing that route, playing that route. The transient head envelope is much smaller than the unprotected case, and head outcomes are quite acceptable. We are seeing the benefit of using stored energy in the pressure vessel as a way of directly addressing the power failure problem. As a solution, the pressure vessel is far more effective in terms of controlling transient heads, and its benefits are experienced across the entire pipe network. Let's view the results as the key nodes report. At node 420, we see a gradual 7-meter dip in head, a totally acceptable situation, quite different to the unprotected case or the air valve case. Closing that report. I will leave you to simulate and explore how well the pressure vessel copes with pump power failure at 7 p.m. I believe you will find it is equally effective.